In this video I want to talk to you about data analysis. Data analysis is a pretty big piece of our class. We are always given at least one set of data that we have to graph and interpret equations on. And so we're going to run through some rules of graphing. We're going to talk about best fit line calculations, interpolating and extrapolating, accuracy and percent error, precision, and the correlation coefficient. And then in another video we'll get into graphical relationships and how to straighten the curve. So why do we need graphs? Graphs are a simple way to present data. When we have a list of data in a table, it's difficult to figure out the pattern. So when we graph the data, we're able to see whether it's a linear relationship, some type of an exponential or power relationship, or maybe we have an inverse relationship, or maybe even a square root relationship. So when we graph the data, we're able to see the relationship much better. And after we've created the graph, we can try to come up with a mathematical equation that relates the variables together. So just some rules on graphing. We always have to identify the variables, and there's two variables. We have the independent variable and the dependent variable. The independent variable is always the one that's on the x-axis, and it's carefully controlled, and the experimenter purposely, which would be you, the experimenter, purposely sets these numbers up in usually even increments, not necessarily even like 2, 4, 6, 8, but sets it up so that we have a consistent set of units. So we might have time, for example, if that's independent, we'll take a time stopwatch measurement every 1 second. So we might plot down every 1 second how fast or how far somebody has traveled. So our data would go 1, 2, 3, 4, 5. And that looks pretty nice. The dependent variable, however, is always what happens due to the independent variable. So again, if we're plotting time and distance, and we're trying to measure a distance every 1 second, we might end up with 2.3 meters and then 4.7 meters. And these numbers are going to be all over the place. They're not necessarily going to be consistent increments. So that's how we identify what the independent versus the dependent variable is. And we always plot the dependent variable on the y-axis. So when we look at a graph, we can identify quickly what the independent variable is and what the dependent variable. Let's see if you can figure out what the independent and dependent variable are in these examples. What if a scientist records the temperature of an unknown solution every 30 seconds? What do you think? I think the two variables we have are temperature and time. And it seems like the scientist is trying to make a measurement every 30 seconds. So when 30 seconds goes by, he makes a measurement of temperature. And so the independent variable would be time, and the dependent variable would be temperature. So which axis would those be graphed on? Time, being the independent variable, would be on the x-axis. Temperature, being the dependent, would be on the y-axis. So you always want to do independent on x, dependent on y. Number 2, the force was measured as the mass was increased. We would want force on the y-axis and mass on the x-axis. As we increase mass, we want to see what happens to force. That makes force the dependent variable. Number 3, graph the population trend of the United States every year since 1980. Well, every year means 81, or actually, since 80 it would be 80, 81, 82, 83, 84. So time, again, would be the independent variable on the x-axis, whereas population trend would be the dependent variable on the y-axis. Graphing circumference as a function of diameter. Whenever we say something is graphed as a function of something else, it means that we're always doing y function x. So circumference would be y, or dependent, and then function of diameter means x would be the diameter. So diameter is the dependent or independent variable. And the last one, acceleration would change as mass is increased. So acceleration again would be on the y-axis and mass is on the x-axis. So identifying which variable would be independent and depending and what axis we'd put those on, that's the first step in doing any type of graphing. So some rules of graphing: when we make graphs by hand, we have to first of all make sure we're neat. We have to use a ruler and probably a pencil, because if we make any mistakes, we don't want to be scribbling things out if we use a pen. So we can use graph paper, which I'll provide to you, or Excel. And we're always going to include a title on there, and the titles don't have to be fancy. If you're graphing distance and time, your title can be as simple as distance versus time. It doesn't have to be anything fancy or creative. Label the axes with the variable names. So obviously you'd want distance on the vertical axis, time on the horizontal axis. You have to use the appropriate units for those measurements, and those have to be in parentheses. So if time is measured in seconds, you put S in parentheses after the axis label of time. And distance, if that's measured in meters, you just use an M and then be in parentheses next to distance. Circle data points when graphing by hand, and I showed you this on a quick video on the Educreations website. I graphed some data, and you'll see that when you plot points on your graph, you want to make sure that the point is tiny. You don't want to make the point too big. Alright, a point is supposed to be a dimensionless object. So when you put a point on your graph, make it so tiny that you could hardly see it, and then you put a little circle around it just to indicate that that is a point there. And that's how we improve our accuracy when we graph data. Then you want to sketch this graph or draw a best fit line. You don't want to connect the dots. That's something that we used to do in elementary school or middle school. We don't connect the dots. We're not doing a line graph. We're doing more of a scatter plot. So if you do this in Excel, you'll see a scatter plot would just have the points, and then if we want to do a best fit line, we can draw a straight line with a ruler through the center of the data. Last, you can calculate the equation of the best fit line by determining the slope and the y-intercept, and that's going to be done for you at a later time on a different video. But the equation is just a matter of finding the change in y values and dividing by the change in x values. And so using some math, you can get the slope, and then figuring out where that line crosses the y-axis, that would give you the y-intercept. And lastly, including some appropriate measures of accuracy, which would be percent error, and then precision, which is the r squared, or the r value. And these two are going to be discussed more later, but when you're using Excel or the graphing calculator, you'll be able to come up with a precision value, which is the r value, pretty easily. So this is an image of a graph that I made in class another year, past year. You can see that the title is distance versus time. You can see down here that I have units of hours, and the axis is labeled as time, and up here it's kind of cut off, but this is distance in kilometers. And when you set up this graph, you want to maximize your space. So I have not tried to put multiple graphs on one sheet, but I've just maximized this, and if I need to make another graph, I'll start with another sheet again. And then the dots are relatively small with little circles around them, so I can identify that those are actually points and they're not just specks of whatever on the paper. And when I draw the best fit line, it should go through the center of the data, and statistically speaking, all the points that are above the line should balance the points that are below the line in terms of distance. But we're just going to come up with an estimate. We just want to eyeball it and put a line through there. The best way to do this obviously would be to use some software like Excel or your graphing calculator, and that'll give you the best slope. But you also need to do this by hand, and so what you're going to do is pick 2 points that are very far apart from each other. Here I picked a point way up near the top of the line and another point here way down near the bottom, and I just put some crosshairs there. And then to figure out the slope, I just figured out what the y values were. This one's 1,000, and this one looks like it's 150, and so I did 1,000 minus 150, and then I correspond to the x values, and this x value down here looks like it's around 9.5, and this one is 1.5, so I subtract, and then last divide to get the slope. And then to find the y-intercept, you would obviously have to extend this downward to see where it crosses that vertical axis, but that's not done here. So what is the best fit line? It's a line or curve that best describes the data. And the statistical process of calculating the best fit line is called linear regression. So if we did this statistically, we'd actually be calling it linear regression. If we just sketch a curve or sketch a line that best describes or approximates the data, that's called a best fit line. And we'll use Excel and we'll use our calculator to do linear regressions. I'll talk more about that in another video or in class. So these are just some directions on doing a linear regression on your calculator, but like I said, I'll show this in another video. A couple other words that we'll run across are interpolating and extrapolating. Interpolating is estimating between data points, while extrapolating is estimating beyond the data points. So here I have a set of data. I have graphed the data. It looks pretty linear. And if we were to put a line through this, let me get my tools out here. This is not going to be a straight line by any means, but if you used a ruler and tried to put a line through that, you would see that the line goes from lower left to upper right. And it should be pretty straight. You're never going to freehand a line like I just did, especially trying to do it with a mouse. But if I estimate between the data points, based on two data points, like let's say this data point and this data point, I can estimate where our line or where the trend is going to be in between those two data points. So when I estimate in between data, I call that interpolating. And then extrapolating would be estimating beyond the data. Here, my data ends right here. I don't really know what happens after that. But if I extrapolate, I can make a guess on what happens in the future based on what was happening previously. So we call that extrapolating. Some other words to describe how we analyze errors involved with looking at data. We say that accuracy is a description on how well the results agree with the true value. We record this as a % error. Accuracy is going to tell us how far off we are in terms of how well we did the lab. You know, if we're supposed to get a certain value, how far away are we? And we always convert that to a % so that we can get a good approximation. And precision is the degree of variability, reliability, or replication. If we could do this over and over and get the exact same results, we're very precise. It also shows us how well our data lines up with itself. If we have a graph and we end up doing a regression and it looks very linear and straight, then we'll probably have a very good degree of precision. We'll use the correlation coefficient, which is the R value, to determine our degree of precision. And that'll be discussed later. So for each of these examples, let's try to look at some accuracy versus precision. Accuracy is how well our data is to the true value. Assume we're throwing darts at a dartboard and we try to hit the bullseye. The bullseye is right here in the middle. Okay, so if we try to hit the bullseye and all of our darts come way out here, are we accurate? Probably not, because we're very far away from the bullseye. Are we precise? Yeah, we're precise because all the data, all the points or the darts, we're hitting the target around the same spot. So in this first case, we would say not accurate, but we are precise. Down in this one, we'll say yeah, we're both accurate and precise because we hit the bullseye and we did it each time. Over here, we're neither accurate nor precise. And in the last one, I'd say we're accurate on this one, but not necessarily accurate on these outer darts. And then precision is lacking a little bit. They're definitely more precise than this dartboard here, but it's not as precise as some other ones. So to show how you calculate % error, it's really, again, just a measure of accuracy, and this equation gives you the general setup of how you would calculate this. So an actual value, maybe this is the acceleration of gravity, 9.8. The experimental value, or calculated, is what you would determine in class. And then, again, you would always divide by actual, and to convert this to a %, you would have to multiply by 100. So that pretty much runs us through the first part of data analysis.